Let's talk about how we can add big numbers on a computer. And by big, I'm going to kind of mean anything that is at least potentially larger than the size of your register. First, let's talk about addition. In general, if I have any two numbers, A and B, A is greater than 0 and B is greater than 0. If C is their sum, C must be greater than A. It is going to be exactly B units greater than A. C must also be greater than B. It's got to be A units greater than B. That's why I want to toss the 0 case, because you can make it all work. It's just that the math gets a lot harder to deal with. I like having nice, clean, simple rules. And if one of them is 0, this really becomes an assignment, not an addition. Okay, let's start out by assuming we're on an 8-bit system. We talked about this when we did the 6502. My add instruction for my example here will add two 8-bit numbers, and that's all it does. There's no side effects. And if we're going to do 16-bit addition on this theoretical 8-bit system, we need a way to store my 16-bit numbers on an 8-bit system. We're going to agree that if I want to store a 16-bit number, I'm going to store them in memory. If I have a number starting at memory location M, the 8 bits stored at M will be the least significant 8 bits of that 16-bit number. The 8 bits stored in M plus 1 will be the most significant 8 bits of that 16-bit number. Since we're doing addition, I do need two numbers. So I'm going to store 1 at M and M plus 1 to give me my 16 bits. And the number we're going to add to that will be stored at N and N plus 1. And remember, M and N hold the least significant portions. If we add two of these 16-bit numbers, my number could be 17 bits long. So the result of my addition, I'm going to store in a memory location called RES and RES plus 1. We're going to keep using the same idea as before. The least significant 8 bits of RES won't be in the location RES. RES plus 1 will hold the most significant 8 bits of the result. I'm going to have this 17th bit, I'm going to call that C. Whether it's 1 bit or an 8-bit register, it's not going to matter. C will always have a value of 1 or 0. So once again, we're going to make this assumption that both our numbers we're adding are greater than 0. Add the contents of M and the contents of N. That's going to give me some result. I want to place the result of that addition into the memory location RES. Now I want to look at the value of my addition. If the result of that addition is less than the contents of M, which is one of the numbers I added in there, then an overflow had to have occurred. If an overflow occurred, I'm going to set C to 1. Otherwise, I'm going to set C to 0. I don't want to worry about having to set this beforehand. That's why right here I'm going to set either 1 or 0. Now, after that's done, I'm going to add the contents of M plus 1 and the contents of N plus 1. I'm going to add the most significant 8-bit portions of my 16-bit numbers and add those together. I'm going to add C to the result of that addition. Whatever I get there, I'm going to place that RES plus 1. Now, just like before, I'm going to look at the value of my addition and see if that is less than the contents of M plus 1 or N plus 1. Essentially, I'm going to go back and look and see, is the result of my addition less than one of the numbers I added to get there? If that's true, we had to have had an overflow. Set C to 1 if that's true. Otherwise, we're going to set C to 0. Now I know I got a valid value in C every time. And we can keep doing that for as many registers as you want to go ahead and do. Let's just show an example of being a 16-bit number on an 8-bit system. You can make it as long as you want. We're just going to keep following the same pattern. Now, another way to do this long addition is kind of like you did in elementary school. we're going to essentially add each digit together and do carries. We know that BCD uses 4 bits to encode a decimal digit. And we can make this scheme work with 4 bits. It's just a lot of masking and shifting to get to the same place. So we're going to modify my definition of BCD a little bit. I'm going to store each digit in 8 bits, 1 byte, which is the same way I read them in. You know, I got my ASCII values I read in. I'm just going to convert those by subtracting ASCII 0 from each byte. When I get done with my answer, it's easy to convert it back to ASCII. I'm going to add the ASCII character 0 to each one of my bytes. And that's all there is to doing the conversion. Now with this first thing we talked about doing, converting to ASCII is hard. You've got to use that double dabble algorithm and actually do the conversion. You know, it is non-trivial to do. This has a little bit more overhead though. You know, one way or another, something's going to be hard. Now, the way I want to make this work, I want to store one of these numbers at memory location M. I want the 8 bits sitting there at M to be the length of that number in characters, or bytes, since they're one and the same. Yes, I mean, I don't really need to have that. You could set up a special flag to show the end of the character. You can't use zeros, because 0 is now a valid character. You'd have to use some number greater than 10. I'd just as soon have the length. I'm going to use it for other things anyway. So the first byte of my number is the length of the number. The contents of M plus 1 will be the most significant digit of the number, just like I read them in. So all I'm doing is adding length to the numbers I read in. That means I can find my least significant digit at M plus the contents of M plus the length. If it has no length, then the only thing there is the length, and the length should be 0. So, okay. Assume I want to add 2 positive numbers M and N. Sort of just like before, I'm going to place the result in R. I'm going to set something called carry to 0. Carry is just another register. For every byte of M and N, every digit, I'm going to start with the least significant, bytes. So I have to skip all the way to the end. But since I have lengths, that isn't any problem. I can do it mathematically. Add together those 2 bytes as well as the carry. That's why we want to set carry to 0 at the very beginning. If the result of my addition is greater than or equal to 10, set the carry to 1, subtract 10 from the result, and I want to store the result starting with the least significant digit of R. Yeah, I mean, all right. There's a little bit of hocus pocus we have to go on here. The least significant digit of R will be the greater of the lengths of M or N incremented by 1. So if I have a 5-digit number and a 4-digit number, I could theoretically end up with a 6-digit number as the result. So my R will, if I added a 5-digit number and a 4-digit number, the length of my result will be 6. Which means if you don't actually have a 1 or something sitting in that most significant digit, you got a leading 0 that you'd like to get rid of. Once they start accumulating, you'll keep getting more and more accumulation. So, go back and look at the result. If that leading digit of the result is 0, I need to subtract 1 from the length, and then essentially left shift all my bytes 1. You know, yeah, there's other ways you could make this work, but that's essentially what you need to do. Like in my example, if I had a 5-digit and a 4-digit number, when I add the 5th digit together, there is no 5th digit on the 4-digit number. So you have to use a value of 0 to make it all work. You kind of already know that. You know, back in elementary school, we learned that, yes, when there's no numbers there to add on that column, you either write the zeros in or just remember that a 0 is sitting there.